So our first speaker here is going to give us a great background into this whole area. Facundo Parodi is with Tryolabs. So this is a machine learning and data science consulting firm based in Uruguay, but having also a presence here in San Francisco. Machine learning and data science, computer vision, and natural language processing. So really fitting into the category here. I'd like to hear a little bit about his personal background. Thesis was developing artificial players for games using neural evolutionary techniques. So really fascinating background there. And today, Facundo is going to introduce machine learning and explore the different types of problems it can solve. Tell us about recent advances in deep learning. Looking forward to that. And how it's revolutionized the entire field of computer vision. So, Facundo, welcome.
Thank you. Okay, good morning. As you're saying, I'm Facundo Parodi. I'm a research and machine learning engineer at Tryolabs. We are based in Uruguay. And today I'm going to talk about machine learning. We are going to see what it is, why are we using it. So as I was saying, we are data science and machine learning consulting firm from Uruguay. We are a 50 people company. And we have almost 10 years of experience in this field, particularly with computer vision. We have worked on several projects, but also some time ago we released Luminov, an open source toolkit for computer vision and specifically for image classification. So the agenda for today is we are going to begin talking about machine learning. We are going to define it. We are going to see what type of problems we can solve with it. And specifically, we are going to see which steps we need to take in order to solve one of these problems. Then we are going to dive into a subfield, this subfield of deep learning. And particularly, we are going to see what an artificial neural network is, how does it work, and how we can use it for image classification tasks. Specifically, we're going to talk about convolutional neural networks. That's the state of the art today. But before we start, I want to ask you all a question that the internet is trying to answer for many years now. What is a cat? And I know this seems like a bad joke, but I actually want you to imagine how a cat looks like. You're probably thinking about something like this. Animals with two pointy ears on the top of their heads, two round eyes, covering different patterns of fur. So I think we are all the same page here. These are cats, but isn't this also a cat? You're only seeing one eye and one ear, but you don't have any problem to identify this as a cat. But what about this one? This is a sphinx cat. These animals don't have fur, but you still classify them, you still identify them as cats. And this one, this is in a really uncomfortable position for me, but it is still a cat, right? And how about this one? You don't see any fur, you don't see the eyes, you only see a black shadow, a silhouette, but you say, hey, this is a cat, we don't have any problem by identifying this. But here you have 4 examples of problems you may encounter when trying to build an image classification algorithm or just trying to build any program that sees, right? Your objects may have another object in front of them. Or maybe there are many, many ways for you to describe the same object. Or your object may be deformed in some way, maybe bigger or smaller, depending on if closer or further from the camera. And you may have different lighting conditions that change the way your object looks like. So even when for us, this seems like a simple problem, it actually has some difficulties to it, right? But let's start from the beginning. What is machine learning? Well, Arthur Samuel defined it as the subfield of computer science that gives computers the ability to learn without being explicitly programmed. And Tom Mitchell gave a more recent, more formal definition that says that a computer program is said to learn from certain experience when working over several tasks and having a performance measure if this algorithm working over these tasks and measured by this performance improves by using this experience. So what all of this is just trying to say is that machine learning is just using data for answering questions. We generally refer to using this data or experience as training our algorithms. While answering questions or performing the task in hand is said to be predicting. So if this is a concept that has been around for at least 60 years, from the 1959 definition of Arthur Samuel, why did it explode recently in the few latest decades? Well, the thing that really changed in the last year is data. We have a lot of it, and it's everywhere. We have really, really slow storage cost. Think about it. You probably have some free gigabytes just for having a Microsoft, Google, Apple, or Dropbox account. And not only that, we have the most powerful and cheapest hardware than ever in history, so we have the means to process all of this information. And even more, not only storing and processing this is easier now, we also have the means to gather, generate all of this data. Like me, you probably have one of these on your pocket, or at least I hope you have it on your pocket right now. And this is a powerful computer fully packed with sensors. We have video cameras, we have GPS, we have accelerometers, you name it. We have all kinds of sensors here. And generally, these devices are connected to the internet. So if you have your image gallery synced with some online storage service, for example, you have your images and videos being uploaded and waiting there for being processed. And not only online storage is available, we have infrastructure as a service. If you don't have the means, your computer doesn't have the power, the computing power needed for running this kind of algorithm, you can just rent it for a fraction of what you would spend if you were to buy this. And we also have massive user applications. We have YouTube, Gmail, Facebook, Twitter, Instagram. All of these huge user-based apps are generating an ongoing, they are generating lots of data that we can use for training algorithms, for example. So what all of this is doing to the world is just transforming it into a machine learning playground for us. But what can we do with all of this data? What type of problems can be solved? Well, we mainly subdivide them in three main categories: supervised, unsupervised, and reinforcement learning problems. Supervised problems deal with learning by example. Here you have a desired output that is known for some sample inputs. And you want to predict this output for new, never seen before inputs. So you may answer questions like, is this a cat or a dog? Is this spam or not? How much does this house worth if it has 3 bedrooms, 2 bathrooms, and 200 square meters? There's a little subtlety here, subdivision, you may say, we do between supervised problems. And depends on the type of output variable we have. If the variable is discrete, like cat or dog, spam or not, we say it's a classification problem. Well, if we have a continuous output, we say it's a regression problem. On the other hand, on unsupervised learning, we don't really have a desired output. We just want to learn something from the data, found latent relationships. An example could be if you have a bunch of images and want to group them together in some way, such that each group has a distinctive characteristic from the others. This is called clustering, and is one of the most common uses of unsupervised learning, but there are plenty more. You can use it for finding hidden correlations, or maybe dimensionality reduction by finding patterns and redundancy in your data and eliminating it. The last type of problem is reinforcement learning problems. Here, we have an agent that needs to interact with an environment through a set of actions. And these actions modify the environment in a way such that it receives a reward, a positive or negative reward. So this is kind of like how we train our dogs. If we want our dog to roll on the floor, and it does, we can give it a cookie. This is a positive reward. While if it doesn't, well, we don't give it the cookie, and this is a negative reward. So we know the type of problem we can solve. How do we solve them? Well, every machine learning project has mainly these 5 steps. The first one being gathering data. So you have to collect data in order to train your algorithms. And this might need some human work. If we think about our classifier for cats and dogs, we should collect cats and dogs images. But not only that, we need to label them. We need to say, well, in this image, there is a cat, and in this other image, there's a dog. And you might have to, you might need some human work to do this. But this is a simple example, cats and dogs. We all know how cats and dogs look like. But if we have, for example, some sample of CT scan images, and we are looking for a tumor there, we may need some expert knowledge. So you have to take that into account depending on the problem you are going to solve. Sometimes this data can come sort of for free, in the sense that you may have an algorithm that works over English text, for example. And you have some sample texts that are written in another language, say Spanish. So you may use machine translation services to take these Spanish samples, translate it to English, and use this also as input. The general rule here is that the more data, the better. Because some algorithms really need a lot of data to perform well, like neural networks. But you mustn't only focus on quantity. Quality is as much as important. Because if you have a lot of data, but it isn't representative of your problem, then your algorithms won't learn. So how can we address this quality problem? Well, this is the next step, data preprocessing or data cleaning. Here you have to ask yourself, is there anything wrong with my data? Maybe I have a house that doesn't say how many rooms it has. Or maybe I have mislabeled examples. I have a cat that is labeled as a dog. Or you may have biased data or unbalanced data. If we think again about the CT scan images example, if this tumor is really rare to find and only 10 out of 1,000 images are labeled as having this tumor, I can just write an algorithm that takes as input any image and says there is no tumor here. And I'll be right 99% of the time. But that algorithm could be useless. So you have to take these points into account. You have to answer this question, is there anything wrong with my data? And then ask yourself another question. Can I fix it? Maybe I can infer a value from the others. Maybe I can infer the square feet of the house by how many rooms it has. Or maybe I can do that, and I just have to remove some data points. Now that we have our clean data, what we have to do is to extract features. A feature is just a measurable property of an object. As an example, we can take this text here, buy cheap drugs from the pharmacy now, and we want to know if this is spam or not. Probably all of you know the answer already, but what are the type of features we can extract from here? Well, we can count the number of words that have vowels changed by numbers, for example. In this case, we have 2, cheap and pharmacy, so we put a 2 here. We can use coding here for the language this text is written. So if we assign 0 for English and 1 for Spanish, in this case, we have a 0. And we can count the number of emojis we have in our text, in this case, 3. So what we've done here is built a vector, this 203 vector, that is just a representation of our input text. And this representation can be more useful for us in order to say if this email is a spam or not. So when we are doing feature engineering or feature extraction, we are not adding more data to the one we have. We are just making it more useful. And generally, if you define good features, you can accelerate the learning process. You can make your algorithms learn faster. But there is really no rule saying okay, this feature is good for this kind of data or for this kind of algorithm, of this kind of problem. So this can really be an art. You have to put a lot of thought into what type of data you have, what type of problem, what could be useful for classifying this the way you want. But generally, we have two steps that are always present here. The first one being variable transformation. Here you take some input and transform it into another form that is more useful. For example, you could have sales data that has a date input. But maybe your sales problem you are trying to solve is more dependent on the day of the week than the specific date of this register. So you may just transform this date, these specific dates, into the weekday and use that as input. The other step is feature creation, when you take a subset of the inputs and construct a new one based on those. This is what we did with our spam example. So we now have features that we can use as input for our algorithm. We have to define what algorithm we are going to choose. So depending on if you have a supervised, unsupervised, or reinforcement learning problem, you have a plethora of different possible algorithms to choose. And again, there is no rule saying, oh yeah, you should use a decision tree for this kind of problem, because any other algorithm could work just as well. But with experimenting with them, trying them, you will gain some insight into what type of problem are best aligned with the type of work these algorithms do. Now that we have our algorithm selected, what we have to do is train it. We want to use our data to predict, right? So the goal of training is just to modify our algorithm's behavior in a way that the prediction that it does are the best as often as possible. And generally, these algorithms have an incremental approach to it. They take some subset samples, they predict the output, and compare it to the desired output that we have. And then, depending on how well they did, they adjust and repeat. And this process continues until we reach some stopping criteria. To know if an algorithm is doing well in its predictions, we need a performance metric to evaluate how well these outputs are. And here you have a lot of possible performance metrics to use, and depending on your problem, some could be better than others. Apart from this internal adjustment that these algorithms do, we have another thing to do. We have to tune hyperparameters. An hyperparameter is just a configuration value that cannot be learned from the data, right? So we have to tune it ourselves. As an example, you may have some algorithm that uses some internal constant for some calculation, and you have to try out some values to find the best. So we now have our algorithm selected, we use our data, we train it, we can start making predictions. So the real difference between training and predicting is just that when we are training, our machine learning model takes our desired output and compare it to their calculated outputs and adjust, right? But when we are predicting, we don't have nothing to adjust. We just want this prediction. So we just return the calculated label. So to recap, machine learning is just an intelligent use of data to answer questions. And it's enabled by an exponential growth in computing power and data availability. We have three big types of problems: supervised, unsupervised, and reinforcement learning problems. And every machine learning project generally has 5 main steps. You have to gather the data, have to clean it, have to extract features, then select and train your algorithm, and finally you can start using it for predictions. So now that we know how machine learning works in general, I want to dive into a subfield of it called deep learning. There is a quote from Arthur C. Clarke that I really like, and I think it's really aligned with the hype that is around deep learning, that says that any sufficiently advanced technology is indistinguishable from magic. And really, we are going to see that deep learning is not magic. We tested it, really. This is not magic. It's just more cleverly applied mathematics. So we first need to define what an artificial neural network is. The first model of artificial neural networks was proposed in 1943. And it was inspired by human and animal brain cells. But since then, this analogy was greatly exaggerated. The processing systems that we all have in our heads are far more complex than anything our neural networks are doing. And we're going to see that. The first idea that came around and really gave us some good outputs was the Rosenblatt's perceptron. This is a simple mathematical operation that takes an input vector, has another vector of the same size here, that's called the weights vector, multiplies them element-wise, and then sums all these values to generate one output value. And then we can take this final value as input for a function that we call the activation function. Rosenblatt used the Heaviside function, or sign function, that assigns a 1 if our input is positive or a 0 if it's negative. And if we take this idea a little further and take some of these perceptrons in an array, call this array a layer, and each perceptron a neuron, and then we take some of these layers and stack them together, there you have it, we have a fully connected neural network. It's called fully connected because each neuron is connected to every other neuron in the previous layer. So what we are left with is a bunch of neurons, each one having its own set of weights, and these weights are the thing that modifies our network's behavior. So they are the ones that drive the calculation and change the network's output. So what we really need to do here is to find the best weights. But how can we do that? Well, we learn from the data. We have all of this data to solve our problem. We can use it for find the best weights. This is the idea. If we define a function that could tell us how close our neural network outputs are from our desired output, then we transform this problem into an optimization problem. We just want to minimize this function called the loss or cost function. And if we are clever enough and define this function as being continuous and differentiable, then we can use gradient descent, an iterative algorithm that uses our function's gradient to adjust the weights values. So we have our definition of neural network. We know how to train them. Why are we using it so heavily? Only the last 2-3 decades. If we say the first model was proposed in the 40s. Well, the history of neural networks is really a roller coaster, like you can see for the title of this slide. It all began with the perceptron, really, in the 60s. It gained a lot of popularity. It was actually believed that it would lead us to general AI, an artificial intelligence capable of virtually performing every task. But this idea was quickly debunked by the XOR function. Here you can see it represented by these 4 points in the plane. And if you try to take this line and move it in this plane in such a way that you divide this plane in 2 regions, and one region has the blue dots and the other one the red dots, I guarantee you couldn't do it, because this was mathematically proved to be impossible. This is what's called a non-linearly separatable problem. And if we think about what a perceptron is really doing, it's just doing a multiplication, an internal product of 2 vectors. And this is representing a linear function. So it's just drawing lines on planes. So it could never approximate the XOR function, this simple 4-value function. So when this was discovered, all this hype, all this popularity around the perceptron just faded, as well as the founding in neural network projects. So we started what later was called the AI winter, this 17-year period when not much happened. But in 1986, a really good idea came around. This is backpropagation. This is an algorithm that uses the differentiation chain rule and allows us to train multi-layered neural networks. So a bunch of perceptrons, like we saw with the fully connected neural network. And this enabled us to train these networks, and we really had good results with it. An example is the Net5, a neural network developed by Jan LeCun and his team that could identify handwritten digits. But we hit a wall. We really were unable to scale. We needed more data. And not only this, we needed more computing power. But if you just give time, technology improves, and good ideas came around. And around 2006, one of these ideas actually came around. The idea is this. If you take all your weights, all your neural network weights, and freeze them except from the last layer, you can train only that layer. Then you can freeze that layer again and unfreeze the previous one, and keep doing this until you train the entire network. And by doing this, you reduce the amount of computation that you need because you are only training one neural network layer instead of the whole layer at a time. So this enabled us to train bigger layers, bigger networks with more layers, or how we call it, deeper networks. And here is when we rebranded this field to be deep learning. And all ideas were revisited, like convolution, that we are going to talk about in a few minutes. And then, 6 years later, in 2012, we really had a breakthrough with AlexNet, a neural network developed by Alex Krzyzewski and his team. And this was the first neural network to really work very well on image classification problems. And the two main differences that this proposal had was the use of convolution and the use of graphical processing units, or GPUs, to accelerate the training process. So they take advantage of this great hardware that were only used for image generation at that time. But how can we use all of this to tackle an image classification problem? How can we use convolution? How can we use all of this? Well, first, we need to understand what an image is. Because here, we all see a cat, we all see a brown cat. But the computer is actually seeing this. 3 big matrices, one for each color channel, one for red, one for green, and one for blue. And each one of these matrices have a bunch of numbers that says how bright a pixel is. So imagine that I were to give you only this and ask you, what do you see there? I certainly doubt that any of you could say, oh, yeah, that's a cat, obviously, right? So how can a computer do this? Well, we need 3 ingredients for this: convolution, nonlinear functions, and pooling operations. And we're going to see each one of them more in depth. First, we're going to see the convolution operator. This, again, is a really simple operation that is defined by a small matrix, in this case 3 by 3, that's called the kernel. And we apply this kernel to an input matrix by taking a region of the same size, 3 by 3, and multiplying each number, the 2 matrices index-wise to generate a new 3 by 3 matrix. Then we just sum all of these values and generate one output value for our output matrix. So pretty straightforward. Then we can just slide this window or this region one number to the right and repeat. We keep doing this, we will generate a row, and if we do this for every row, we generate an output matrix. So now you can clearly see the cat, right? Well, we have to dive a little deeper. let's see an example. Let's see what happens when we apply this kernel to our brown cat. We generate this output image called a feature map or activation map. And we can see some pretty interesting things here. Like the cat's eyes are bright white, or we can really see the edges of the image. We can clearly see the ears, the paws, the whiskers. Some of these edges are being enhanced. So you can think of a convolutional kernel, a convolutional operator with a kernel, like a feature extraction tool. Because we are just making some characteristic of our image stand out from the rest. So let's think again how we can use all of this to classify cats. If we just define a kernel that would look for triangle shapes for the ears, another filter that looks for circles for the eyes, and another kernel that looks for this horizontal pattern in the cat's fur, we can just build a small algorithm that says, well, look at the activation map of the triangle-shaped kernel, and if you have two sections on the top, you have two ears, the same for the eyes and the fur. Well, we have a problem, right? Our fur kernel doesn't activate with our Sphinx cat. It's okay. Let's get rid of this filter and only use the other two. Well, let's get rid of the restriction that we need two ears and two eyes. Well, this doesn't work, right? This really doesn't work. So what's the problem? Well, we are not defining the best kernels here. So how can we do that? Well, we learn from the data again. The convolution operator is just a bunch of multiplications and sums. So they are all continuous and differentiable operations. We can still use gradient descent for this. So what convolution really does to our traditional machine learning pipeline is to get rid of the feature extraction part. We don't need to build these features because our networks are going to learn them, learn by themselves what filters are best for the problem, for solving the problem. Okay, this is what convolution does, learns features. What about the nonlinear activation function? Well, again, if we think about the operations that the convolution is doing, they are all linear. So we still have the XOR problem, because compositions of linear operations gives you a linear operation. So we are still drawing lines on planes. But if you remember by the perceptron definition, we were taking our value and using it as input for an activation function. And Rosenblatt used the Heaviside function or sine function, but we can use whatever we want. Particularly, we can use a nonlinear activation function and add nonlinearity to our model. So, which function to use? Well, for a long time, we were using sigmoid functions, or these characteristical S-shaped functions, like logistics and hyperbolic tangents. But we discovered that these functions have some problems with our gradient descent approach. So now the state of the art is to use rectifier linear units, or ReLU. This is a really simple mathematical operation that takes the maximum between 0 and our input. So this is really fast. We can calculate a lot of this in our graphical processing units in a matter of milliseconds or microseconds. So let's see an example. What does our ReLU operator does to our activation map? As you can see, it gets rid of some of our details that we don't want, like the background or some colors on the fur pattern, because we were looking for edges. And the edges are now clearly seen. We really see the eyes and the cat's ears. So this helps understanding even more what our activation maps are representing. Okay, the final ingredient, pooling. Remember that I said we have the most powerful hardware than ever in history? Well, the computing power isn't infinite. We still have to be clever in the way we define our models and try to minimize the amount of computation that we need. A way of doing this is using a pooling operation, the most common one being the max pooling operation, where we subdivide our input matrices in same size regions, in this case 2 by 2, and just take the maximum value of each region and put it on an output matrix. So what we did here is to generate a new output matrix that is 4 times smaller than our input. So we need 4 times fewer computations. And this is used for this. We use it for dimensionality reduction, but it also has a great property, that is making our networks invariant to small transformations and distortions and translations. As an example, you could think about our run cut again, and if we move it 1 pixel to the right, these 2 by 2 regions are not going to change that much after we pass the max operation on them. And if you apply a pooling operation several times, then it could be even more invariant. So let's try to put all of this together. We have our input image represented as an RGB set of matrices. We apply some set of filters to generate this set of activation maps. And then we apply a nonlinear function, for example, a rectifier linear unit. Now that we have these activation maps, we can then apply a pooling operation and shrink our dimensions. And then we can just repeat this and apply another convolutional layer, another nonlinear function, and another pooling. And if we keep doing this, we will get a small enough set of activation maps that we can then use as features. So we can take this, flatten it in a vector, and then just apply a vanilla fully connected neural network. So what we have done here is to subdivide our problem into a feature extraction part and a classification part, just as the traditional machine learning pipeline. The only difference is that this is not going to train automatically. If we think about what each layer of convolution is doing here, the closest ones to the image, the ones that are here working over the image, are going to try to find some simple characteristics of the image, like edges or lines or color blobs. But the next ones are not going to work over the image, are going to work over our activation maps. So they can codify some more complex relationships, like looking for a curved line, like a circle, that has yellowish color inside. This could be our cat's eye. And you getting further and further from the image, and each convolutional layer is going to represent some more complex and abstract concept, until we reach some point when we can say, okay, this is an ear, this is an eye. If we have 2 ears, 2 eyes, we have a cat, right? But this is all learned by this classification part of the problem. So we need just one more thing to discuss. How do we train this? Well, image classification is just a supervised problem. So we need examples. We need images of our targets, in this case, cats, and labels. So then we can train it with backpropagation. So let's see an example. We have our cat friend here that we can use as input for our convolutional network and get a prediction out of it. In this case, it says dog. And then we can use this prediction and this label as input for our loss function. And in this case, we get a value that is greater than 0 because these two doesn't match. So now we can use backpropagation here and adjust the convolutional network weights in order to improve our prediction. And if we do this long enough, we eventually will generate the correct prediction. So now our loss function is happy. It says, okay, 0, these two are equal. So what we need to ask ourselves is, convolution is really that important? And the answer to this is that, yeah, it is an important discovery. Because just to give you some context, A few years ago, there was a competition called ImageNet, an image classification competition, that used millions and millions of images and has around 20,000 possible labels to predict. Until 2012 here, the best algorithms were having around 25% error rate. So this means that 1 out of 4 images were being misclassified. So this is not very good. But in 2012, AlexNet came around, and it really obliterated the competition. They dropped this 25% error down to 15. And in later years, the top competitors were all using convolution and GPUs, just like Alex Krzyzewski's team. And in just 3 years, in 2015, we surpassed human performance. So this is really something that doesn't happen every day. This is really a game changer. And since then, this has not stopped. We have deep learning everywhere. You have it on your phone when you give orders to it. Or we use it for translating text on images. We are even using it for generating art or game AI players that beat humans in chess and Go and and recently StarCraft. So not only this has not stopped, it's here to stay. We have more data than ever in history, and it's still going strong. We have new architectures, new ideas being presented every day. And not only that, we can make it real in really short spans of time by using frameworks that help us maybe try an idea in a matter of minutes. And we have the computing power to test these ideas by training these new architectures. If you don't have it on your computer, as I said, you can rent it for a fraction of what you would spend by buying it. And we have these real big players. We have Microsoft, Google, Facebook, DeepMind, all of these big players that are investing a lot of effort to get better and better. And we have a great community around this that it's always giving good ideas. So I have 2 main takeaways from this talk for you. The first one being that machine learning learns from your data. So it's really going to be as good as your data. The best algorithm out there, take the best algorithm out there, feed it bad data, I guarantee you will have bad results. So you have to really spend a lot of time cleaning data and understanding the problem to know if you are going to do feature extraction, for example, you have to really take a lot of care there and devise which features are the best. The other key point is that machine learning and deep learning specifically is really making big breakthroughs in every field you may imagine. In medicine, in control systems, in game AI, in computer vision. You really have it everywhere. So I suppose if you are here, it's because you want to learn more about this, but if you are not using it right now or considering using this, especially in vision problems, I think you certainly should be. So as a final note, if you want to know more about these topics, there are really good resources out there, like Google's machine learning crash course or Stanford online courses on machine learning and convolutional neural networks. And you also have our blog, Tryolabs blog, where we talk about how we use this kind of technology to apply it to real-life problems. And you have Luminov also if you want to play around with image classification problems, train your own networks, and that kind of thing. And obviously, you have this entire summit to go to other presentations in the fundamental track or other tracks to know more. So that's all I have. I want to thank you all. And if you have any questions, please feel free to ask them.
Yeah, we have quite a bit of time for questions here because lunch doesn't start till 12 o'clock in the showcase room. Please come up to the microphone so everyone can hear the questions. It was an amazing talk. It is amazing to me to see after 30 years of trying to use algorithms to classify images and totally failed that within 3 years, deep neural networks have kind of exceeded the human capability. So first question.
Yeah, hi. I had a quick question regarding the training of the deep neural network. So you talked about it being trained layer at a time using backpropagation.
Yes.
So typically backpropagation, you are propagating to the entire all the layers essentially at a time. So when you say that, how do you train the intermediate layers? Like, what is your specific target, and how are you freezing the layers? Can you go into some detail on that?
Yeah. The idea of freezing layers was the way we were training neural networks at the beginning of this century. But since then, we are not doing that anymore because we have now the computing power that we need to train the entire network at the same time. So the way that backpropagation works in this way is that if you think of the neural network as a function, that's what really is, and you calculate the error rate that you have on your output, then you can use this error rate to adjust based on the gradient of your function. So each layer works. You can think of each layer as a function that takes the previous layer outputs as inputs. So when I said that backpropagation uses the differentiation chain rule, what I try to say there is that when you are trying to calculate how much to add or to add to a neuron's weight, what you are doing there is calculating the gradient on the last layer. But then you have to calculate it for the previous one. And then is when you use the chain rule. You say, well, the gradient of my previous layer is the value of the next one, the value of the gradient on the next one multiplied by this layer's gradient. So it all goes down to just applying that rule again and again until you reach all the layers of the network.
Okay, so does that mean that you are not trying to train a layer and then freeze the weights and then freeze the others? You are still propagating all the way.
Yeah.
So it's just a matter of computational power being available to do that.
Yeah, exactly. The freezing strategy was a way to train networks when we didn't have the enough computing power to train the entire network at the time.
Let me ask a follow-up question and get
Yeah.
to you. What is a typical number of layers that people are using in today's networks, given today's computing power?
It depends entirely on the problem and the architecture that you're really using. As I said, every day we have new proposals and new architectures, and they are getting deeper and deeper. So you maybe since I don't know, the most common one to use is, for example, a ResNet 50. It has 50 layers. But a few years ago we were using 16. The most common one is BGG 16. So this is something that is really changing a lot all the time. And right now there's also the question about, do we need to go deeper or wider? So you are seeing these kind of changes now that maybe we are not using more than 50 layers, but we are using more wider networks.
Yeah, I have a slightly different question from what the others had. So there's a scratch for programming like that. If you have a scratch for machine learning or deep learning, make it more tactile and intuitive versus all the math and the complicated number crunching. Why aren't people working on that yet? Is it too early? Is machine learning going to involve a lot more than? Because in the internet, we don't see the intricacies. They're all plugins and buttons. But in machine learning, you have to really get into the complicated math if you have to tweak it, right?
Yeah. Sorry, I didn't understand what you mean by scratch there.
Oh, okay. It's a very user-friendly programming language for kids.
Sorry. I know what that is.
Yeah, so it's 6-year-olds can program.
Okay, so depending on the type of problem you need to tackle, you may need to go deeper in the sense that you really need to go low level, understand what these networks are doing and changing sensible parameters that are really difficult to abstract in something like
A user.
a user
Yeah,
interface,
okay.
right? But I mean, this is a matter of time because with cutting-edge technology, with these latest advancements, you have to go that deep.
Right.
Because you are trying new things.
Yeah.
But with time, these kind of ideas are getting more generalized, and then you can start doing that kind of like user interface that can change this. Actually, in the way we work, we do see that change, not going to our user interface, but instead of using low-level programming like maybe use TensorFlow right from the scratch, you can use Keras. That is another, it's a layer over TensorFlow that you could use, and it's more intuitively, but doesn't let you tweak some of the details that you could if you use.
So it comes in a platform, and we can't really, it's not transparent, so we have to live with that. We can't really.
Yeah.
Okay, I get it. Okay, thank you.
Thank you.
I will not accept that answer. We'll get better. I'm Walter with Walmart.com, and I'm really more on the line of what she's saying. I need it to be like user-friendly because I'm trying to implement that stuff now, especially in our e-commerce center. So my question is, it's actually like two questions. So this morning they talked about automated machine learning, right? So you're talking about like the supervised and unsupervised, and they mentioned that he mentioned the teacher deploying the students, and then if they're not good enough, they come back. Do you still feel like there's loss? I mean, how do you? I'm not asking for the implementation necessarily, but the loss function or some sort of comparison for that AI teacher to be able to say that's not it. Is that what it's using at that point?
Well, when today on the keynote they were talking about AutoML, the thing is that
I was very excited.
Yeah, that's a really good keynote. The thing there is that you do need some way to compare different algorithms in an objective way, right? So when you use AutoML, you really are using some metric to define which of your solutions is going to perform better. In this, we saw two different approaches, right? The one where you train all these networks on the students and then like average the weights. It's a little more complex than that, but that's the idea. Then what you would do there is to check, for example, you could use a mean square error performance metric to see if you are doing better or not. So you would still need this performance metric because you wouldn't know which of your students is doing better, right?
My other question is, so I don't really have access to NVIDIA or GPUs currently because we have a cloud instance and an on-prem instance, right? So this is kind of like this distributed, where I'm going to do some of my stuff, major stuff in the cloud, but I'm going to use some of my stuff locally.
Oh, yeah.
Is there any limit? I mean, I haven't really done. I'm about to dive into that like right now, but how can I take advantage of those capabilities without the GPU capability in the cloud or even locally? Like I literally just, I have an Azure instance and I can spin up some stuff, but on-prem I may have some minimal server capability.
Okay, so depending on the type of problem you're going to work on, you may not need a GPU in the sense that generally we use GPUs for vision tasks because we really need to process a lot of information. An image really has, especially a high definition image, has really a lot of values that you have to compute. And even though you are shrinking your dimensions with pooling and so, you really need a lot of computation power. But if you are going to work with things like tabular data, more like sales data, or the examples I gave with house value market, then you won't need that much computer power.
I have images there.
Okay, so your images. Okay, and you have then a lot of instances, but you don't have GPUs.
Right.
Okay.
We don't have that yet.
Okay.
I mean, we do in Walmart, but actually we don't
Yeah. I understand that. Okay. I really would suggest that you get some. Because the thing is that although you can,
No benefit. I mean, just
I mean, you have some frameworks that you do distributed computing, but if you are only using CPUs and you are heavily using images, you are probably going to hit a bottleneck there because GPUs for this kind of computations are 2 or 3 magnitude orders better than CPUs. Okay, so you could do that. I wish you luck. I really suggest you get some GPUs.
I was wondering if you could discuss a little bit about the error rate currently of machine learning in systems where a single error is highly, you can't have like it leads to somebody's death or something like that, versus like a very custom tuned piece of software written just for that application.
Okay. I don't have real personal experience with that specific kind of critical software. What I can say is that you have a lot of time invested in trying to understand what your algorithm is doing there. Because in that kind of critical system, you cannot just say, okay, take this black box, use it, and just go with it. So you add another step there to the five that I mentioned, that is try to understand what your network is doing. And we have advanced a lot in the last years with this. We have really good methods to try to understand what each layer is doing and what type of attacks you could do to confuse the network and such. I personally have tried some of those, and they are really great. But you have one problem. They are great for a subset of layers, in the sense that if we see what the activation maps of the first layer are, we are all going to understand them, and we are okay. The second layer is just something a little rarer, because you are not working with the images that is the thing we are understanding. You are working with these activation maps that, when I showed you the activation map from the cat, okay, that one you still see the cat. The next one you won't. So we have means to check, for example, what type of image does activate even more the second layer neuron, right? So that's the way we are currently understanding this type of networks. So when we talk about the error rate that you would get, it's not sufficient to just only say, okay, we have a 99% error rate on the validation set. Okay, but you still wouldn't trust in that kind of algorithm, just because you get 99% accuracy in a subset of your problem, right? So you really start this investigation on the network to really understand and not only achieve this error rate. You want to achieve that and understand why is that happening, right? So
that's interesting, because I do a lot of work with medical startups, and a lot going on in machine learning and medical startups. And there is a lot of concern about hidden layers and not understanding what's inside. So I see a lot of adoption now just being as an advisor rather than a decision maker.
Yeah.
But it's still a human that takes the data, maybe concentrates on a certain area. I have one more question for you. I've seen a lot of work more recently in competitive neural networks to train faster, like the Go, the champion. Can you say something about that?
This is a field that's really, it's not mature enough, I would say, for production-wise, because as well as with what I was saying just now, we don't really understand how exactly these networks are learning, in the sense that, we know we have a discriminator and we have another network is learning from that, or maybe we have competing ones and just beat themselves. But what we don't know if by beating themselves, they are going to beat other agents, right? So there's still this question about self-learning. Is it good enough to learn how to beat every other player, or just the way the network actually learn? So I think it's an exciting field. We are really having good results with it, especially in game AI. I think we need more time to see it really develop enough to use it maybe on medicine, for example, or fields like that.
Okay. Very good. Well, thank
Okay.
you
Oh,
very much.
thank you.
Excellent talk.